Good afternoon, everyone. Thank you all for joining my presentation. I am Bram. I'm a PhD student at Ghent University, Belgium, and my research is all about valorizing lignin into a highly reactive polyol for a wide variety of applications, such as in polyurethanes or in polyesters, but specifically for my project for self-healing boronate ester gels. So for all people who are not familiar with lignin is a cross-linked biomacromolecule which typically can be found in all vascular plants. And today, lignin is not being used as a high-quality reactant, but rather as a cheap filler material in, for example, concrete and resins to increase the bio-content. Now, there are some challenges when you want to work with lignin. And for example, lignin is composed of 3 monomers or monolignals, which can bond together via different linkages. For example, we have, in this case, the beta-O4 bond, we also have the 4O5 bond, and we also have the beta-beta bond. And this heterogeneous structure results in a rather low and non-uniform reactivity. Moreover, it is also challenging when you want to fully characterize lignin. And for example, when you perform carbon NMR, you will obtain a very complex spectrum, and literature is currently lacking assigning each peak to each carbon atom. Another example is a size exclusion chromatography with a conventional gel permeation chromatography with detectors such as a variable wavelength detector or a refractive index detector, where we can only measure or quantify the relative amount or the relative molecular weight instead of absolute molecular weights, because we are lacking the availability of certain lignin standards. Often we use polystyrene. And another one, which is actually very important, it is not merely using lignin as an alternative to non-renewable fossil-based chemicals. You also have to make sure that the applied chemistry is sustainable as well. So for example, if you want to incorporate lignin into a certain resin and you have to modify the lignin, then you should make sure that the modification is green and sustainable as well. And therefore, in the following 20 minutes, I want to talk to you all about the oxyalkylation. So oxyalkylation, also called etherification, from a historical perspective, it's already been performed many times by, for example, organohalides in the Williamson ether synthesis, or ring opening of epoxides. But of course, I think it's very obvious that, for example, ethylene oxide, it's a dangerous chemical. It's not sustainable, not green, and it's a toxic gas. So we should try to avoid such chemicals as much as possible. So that's why I propose the oxyalkylation with cyclic carbonates, in this case ethylene, propylene, and glycerol carbonate. Now the first two, ethylene and propylene carbonate, are already studied in, you can find some studies where they used these chemicals to modify lignin. But the last one, the glycerol carbonate, is definitely not sufficiently investigated, while it does result in some nice possibilities. So when we want to look at the results, we first have to take a dive into the mechanism. So lignin is composed of phenolic hydroxyl groups. After deprotonation, there can be a nucleophilic attack on one of these two electrophilic carbon atoms with the release of carbon dioxide, resulting in a 1,2-diol or a 1,3-diol. But lignin is not merely composed of phenolic hydroxyl groups, it also contains aliphatic hydroxyl groups. And here the reaction pathway is a bit different. So there is deprotonation, followed by a nucleophilic attack on the electrophilic carbon atom of the carbonyl bond of the carbonate structure. And again, we obtain a 1,2-diol or a 1,3-diol, but in this case we also have an aliphatic or a linear carbonate structure incorporated into the lignin. And in this case, we don't release any carbon dioxide. In general, the majority of our products will be 1,2-diols, because then the nucleophilic attack has to be on the less sterically hindered and favorable carbon atom, and therefore we obtain 1,2-diols. But when we talk about the reactions, we also obtain side reactions in most of the cases. So when there can be some polymerization on top of the newly formed hydroxyl groups. So a hydroxyl group can again react with another cyclic carbonate functionality, and thereby we get like this tree, these branches of trees going wider and wider, whereby the hydroxyl group content will increase as well as the molecular weight. So this is definitely a side reaction. Another possibility is that you get some kind of internal transesterification, thereby shielding your 1,2-diol functionalities, resulting in this cyclic carbonate structure. This is definitely an unwanted reaction, because we are shielding our 1,2-diols, which we can further use in polyesters and polyurethanes. So then we come to the oxyalkylation setup. Very easy. We take a round bottom flask, we add the lignin together with a certain amount of catalyst, in this case it's potassium carbonate, and we add an excess amount of glycerol carbonate. And we use an excess of glycerol carbonate because glycerol carbonate acts as a reactant as well as a solvent. So instead of adding an additional solvent, the solvent has to be green, has to have a high boiling point because we are doing these reactions at 175 degrees. That's difficult to find. Therefore, we just use glycerol carbonate as a reactant and a solvent. Then we perform the reaction under nitrogen gas atmosphere. Why? Because any moisture would lead to ring opening of the cyclic carbonate. Then after reaction we precipitate the lignin, followed by a filtration, and eventually the filter residue is our modified lignin. So then we come to the first parameter I want to discuss, and that's the catalyst. When we take a look at the organosolv lignin that I've used in my study, it contains a rather high content of aliphatic hydroxyl groups with 2.61 millimole per gram and phenolic hydroxyl group content of 2.43. There are also carboxylic acids, but that's definitely a minority, so I will not discuss this in detail in this presentation. Now what we can see that after reaction at 175 degrees for 30 minutes without the catalyst, no catalyst, we obtain an increase in molecular weight, but our phenolic hydroxyl groups do not decrease. And that's something we didn't expect. We expect when we perform the oxyalkylation that the phenolic hydroxyl groups that they decrease because they are turned into aliphatic hydroxyl groups. Moreover, we expect that the aliphatic hydroxyl groups should increase, yet here we see a decrease. And this is of course likely because of the lignin is a biomacromolecule and therefore it is not thermally stable. And without the catalyst, some other reactions can occur, perhaps some condensation reactions, thereby increasing the molecular weight. So it's definitely necessary to add a catalyst. And when we look at all these catalysts, there's something interesting about the DBU. A DBU, this molecule, is a catalyst typically used in literature to oxyalkylate lignins and tannins, often with ethylene carbonate or propylene carbonate. But we should definitely try to avoid using DBU as it is a toxic chemical. It's also a non-sustainable chemical. So therefore, we take a look at potassium carbonate, and potassium carbonate has a very high aliphatic hydroxyl group content of 4.59, higher than the DBU, which is very promising, of course, so we can use potassium carbonate instead of DBU. Now, the aliphatic hydroxyl group content of 4.60 millimole per gram, what does it contain? Well, it contains all native, unreacted aliphatic hydroxyl groups, as well as all newly formed aliphatic hydroxyl groups. And because the hydroxyl group content, we determine it by using phosphorus NMR, we cannot distinguish between the two signals. They completely overlap in the phosphorus NMR spectrum. So all we can say for sure is that the potassium carbonate, that the phenolic hydroxyl groups are completely converted, the carboxylic acids are completely converted as well, but we cannot say anything about the aliphatic hydroxyl group content, the native aliphatic hydroxyl groups. They might have reacted, might have not reacted. We cannot say at the moment. Something else we noticed during our reaction is that there is a viscosity increase. And so the reaction mixture, when I want to transfer it to precipitate in the pH 2 water solution, it is obvious that the reaction mixture has increased in viscosity. So therefore we did an experiment with potassium carbonate and glycerol carbonate at elevated temperatures but without lignin. And so prior reaction, the blue line, we can see there is no signal in our GPC. So we cannot determine any molecular weight. And that's because glycerol carbonate is such a small molecule that it takes a very long time to elute from our GPC columns, and eventually it gets lost in our system peaks. So we don't have any signal. After reaction, we clearly obtain a rather high molecular weight molecule fragment, oligomers, which is because of the polymerization of glycerol carbonate. On the right, we did prior and after reaction as well, some measurement, NMR measurement, proton NMR measurement. And in the blue, we can definitely see these signals correspond to the glycerol carbonate molecule. After reaction, there is definitely some broadening of our signals typical for polymerization. So in conclusion, about the catalyst, potassium carbonate results in the highest aliphatic hydroxyl group content, which is of course very beneficial because then we don't have to use the toxic DBU. And there is formation of polyglycerol carbonates, resulting in a viscosity increase of the reaction mixture. And that is actually very important, the viscosity increase, when we discuss the next slide, the temperature. So with the temperature, we tested 120 degrees, 150 degrees, 175 degrees, and we obviously see a molecular weight increase with higher temperature, accompanied with a higher aliphatic hydroxyl group content. So in the end, we can say, okay, we need to have a high temperature. But this temperature results in a high aliphatic hydroxyl group content. We're very happy about that. But it also increases the viscosity of the reaction mixture. And I did an experiment at 200 degrees, but I cannot show you the data because I was not able to generate any data. Because it was impossible at 200 degrees after 30 minutes to do the workup procedure or to collect any material. It was like very solid-like. So we just had to throw it away. It was impossible to collect any material. So we need a high temperature to have a high aliphatic hydroxyl group content, but too high, the temperature is limited because of the increase in viscosity. Now, in order to reduce the viscosity increase during reaction, we added an additional solvent, in this case our 1-butylpyrrolidine 2-on. And why did we choose this solvent, or this solvent, this chemical, is because 1, it is a potentially bio-based solvent, and 2, it doesn't react in our oxyalkylation experiment. When we perform this reaction with the additional solvent at 175 degrees, we get a similar aliphatic hydroxyl group content of 4.60 millimole per gram. So there is no benefit of adding an additional solvent. It only makes the reaction mixture more complex. When we perform the reaction at 200 degrees, we are able to collect the material to precipitate the lignin because of the reduced viscosity because of the addition of the solvent, but we get a very low aliphatic hydroxyl group content. And that is because a high temperature, you also have to take into account that lignin will depolymerize. And especially the lignin I used, it is pulped at 170 degrees. So when you go above the 170 degrees, there might be some breaking of certain bonds, certain linkages. And that's the case, what's happening here. And this is also proven by HSQC NMR. So in the end, we got a nice set of conditions we can apply to obtain a high aliphatic hydroxyl group content, namely the 175 degrees centigrade for 30 minutes with potassium carbonate as a catalyst. But now we have to think, is this sufficient? Are we happy with the 4.60 millimole per gram? Well, we can make a calculation of the hydroxyl group content that we expect after oxyalkylation. And so we can see, or we can take the total hydroxyl group content and we multiply it by 2. Why by 2? Because every hydroxyl group becomes 2 hydroxyl groups because of oxyalkylation of glycerol carbonate. But you also have to take into account that 1 gram of lignin, let's say you start with an initial 1 gram of lignin and you modify it, that it also increases in molar mass because you add glycerol carbonate on top of it. So in this case, 1 gram plus the aliphatic hydroxyl groups times the molecular weight of glycerol carbonate, 118 gram per mole or 0.118 gram per millimole. And then we also have the phenolic and carboxylic acids, and we have to multiply these two by the molecular weight of glycerol carbonate after release of carbon dioxide, so minus 44 gram per mole. And this results in an expected hydroxyl group content of 6.90. So 4.60, 6.90, that doesn't match, so we are not happy at all, and so we have to investigate some more. And therefore we used FTIR. And it is immediately clear in FTIR that we do not have any signal at 1740 inversed centimeters. And typically this signal corresponds to linear or aliphatic carbonate functionalities. But when can we have such structures in our lignin? Well, that is when the aliphatic hydroxyl groups react with glycerol carbonate. But since we don't have any signal, we can say that the aliphatic hydroxyl groups in lignin that they do not react with glycerol carbonate, which is, for example, different than when you use ethylene carbonate. In ethylene carbonate, aliphatic hydroxyl groups, they do react, but with glycerol carbonate, they do not react. And this was further proven or confirmed with carbon NMR. Something else that we notice is that there is a signal at 1790 inversed centimeters, and this is typical for a carbonate bond in a cyclic carbonate, a carbonyl bond in a cyclic carbonate structure. So, for example, this structure here. So then we perform the hydrolysis by opening this ring structure by working in a 0.2 molarity potassium hydroxide in ethanol solution. We reflux at around 79 degrees for 15 minutes. And then we measured the hydroxyl group content before and after hydrolysis. And then we were able to see that if you do the reaction, the oxyalkylation at 150 degrees centigrade, we get the cyclic carbonate content of 0.94 millimole per gram. But if we do the oxyalkylation experiment at a higher temperature of 175 degrees, we get a cyclic carbonate content of 0.42 millimole per gram. So what do we have to take into account when we perform the oxyalkylation of lignin is 1. You need to have a sufficiently high temperature to sufficiently increase the aliphatic hydroxyl group content. You also have the high temperature is necessary for reducing or inhibiting the formation of this cyclic carbonate structure, shielding our 1,2-diols again. But you cannot go too high in temperature because then you get difficulties in the work procedure because of the viscosity increase. So then we can go to the boronate ester gels. And what do we need for the boronate ester gels? Well, we need the 1,2-diol, which we just made, and a crosslinker. In this case, a boronic acid crosslinker. Actually, it is the benzene 1,4-diboronic acid crosslinker. So it's a very simple, short crosslinker, commercially available. And in the case of the 1,2-diols, we have to determine the content. And so what do? We take the final aliphatic hydroxyl group content and we subtract the initial aliphatic hydroxyl group content from it because these aliphatic hydroxyl groups, they do not react. Remember the FTIR spectrum. And then, of course, we divide by 2 because we want a diol, not an alcohol, but a diol. If we put all these reagents together in an alkaline environment by just adding sodium hydroxide, for example, then the reaction is shifting to the right and we get the boronate ester structure. And so here you can see on the left, this is unmodified lignin, which obviously does not crosslink. Then we have modified lignin, which does crosslink, as you can see here with the vial turned upside down. Here we also made a gel, disc-shaped gel, and we made a cut into it. And after 1 hour you can clearly see that there is still a visual cut, but that there is also some self-healing already present. But I am an engineer, so I want to quantify this behavior, and so I started doing rheology. So I took my disc-shaped gel and I put it on the rheometer, and then I waited for 10 minutes. So this is some kind of rest time to make sure the the gel can settle and it can acclimatize to the set temperature of 25 degrees. Then after 10 minutes, we started doing an amplitude sweep and thereby always increasing the amplitude a little bit more. And so in the beginning, you can clearly see that we have a storage modulus higher than a loss modulus if we only take a look at the purple lines, which means that it is a cross-linked system. We're still in the linear viscoelastic region. After a while, when the amplitude is increasing and we are deforming the material more, we go outside of the linear viscoelastic region. We still increase the amplitude, and after a while, the storage modulus is lower than the loss modulus, meaning that the material is now completely deformed. Afterwards, we immediately do a time sweep whereby we notice there is an instantaneous self-healing behavior of our gel. With the storage and the loss modulus similar to the measurements prior deformation. If we, however, change the amount of crosslinker, so the stoichiometric ratio of 1,2-diol boronic acid functionality, we get a different behavior. We get lower loss and storage moduli, as well as partial self-healing behavior, not fully self-healing behavior. So to summarize everything, what are the optimal reaction conditions when you want to perform an oxyalkylation with glycerol carbonate, for example, to further apply in polyesters and polyurethanes? You need to use potassium carbonate as a catalyst, together with a reaction temperature and time of respectively 175 degrees and 30 minutes. What are some insights that we obtained? You will always have these final cyclic carbonate functionalities present on top of lignin, thereby shielding your 1,2-diols. However, you can inhibit this reaction, this internal transesterification, by working at an elevated temperature, especially the 175 degrees centigrade. You cannot go much higher than the 175 degrees because of homopolymerization of glycerol carbonate, thereby increasing your viscosity. Then what about the gels? Well, we were successfully in synthesizing boronate ester gels with short, simple crosslinkers commercially available. Moreover, those gels can have a fully self-healing behavior depending on the amount of crosslinker. Now, a shout out to all the people who helped me, because of course I did not do this research on my own, thanks to my promoters and other people who have helped me during my research. Thank you all for your attention, and if you have any questions, feel free to ask them, contact me, especially if you want to oxyalkylate your lignin yourself. Thank you.